Hello, welcome to a new lesson of the study of the Fourier Bessel series. We have made a first lesson where we introduce three definitions for the Fourier Bessel series of a function, okay? Because there are three special cases to do this. In this case, I just wrote two of them, right? They are defined by these conditions that we have here. For the first case, we have this condition, and for the second case, we have this other condition. And that is because I'm going to solve an example, right? I'm going to represent a function f of x, and I'm going to do this for these two cases, okay? So the main idea of the Fourier Bessel series is that we can express any function f of x defined on an open interval 0, b in terms of a linear combination of Bessel functions. And recall that these Bessel functions are the solutions of the parametric Bessel equation. Okay, these are not just the solutions of the Bessel equation, but the parametric Bessel equation. That's why we have this alpha I here. Okay, so the thing here is that if we have that the numbers alpha are defined by this condition, then the Fourier Bessel series of the function f of x in the open interval 0, b is defined as this expression over here, with the coefficients defined by this formula that I just wrote here. Okay, but in the other way, if we have this condition to define the values alpha, then the coefficients will be calculated with this other expression that we have here. And we are going to see these two cases in the next example. We are going to define f of x equals to x, and we want to express this as a Fourier Bessel series, right? This is going to be defined in the interval 0, 3, and that immediately tells us that, well, b is going to be equal to 3, okay? And in our example, the frontier condition will be that the Bessel function of order 1 of alpha b is going to be equal to 0. Okay, but we said that b is equal to 3, right? So this will be the Bessel function of order 1 evaluated at 3 alpha. Okay, so that will be the initial condition or the frontier condition. Okay, so we know that we can express f of x as the linear combination of the CIs and the Bessel functions. So that is going to be the sum from I equals to 1 up to infinity of the CI times j sub 1 of alpha I x, right? Because in our example, the n is defined to be equal to 1, right? This is the n. I mean that the n in general is defined to be the order of the Bessel function that defines these values alpha. So this n is telling us what is the order of the Bessel functions that are going to define the function f. Perfect. So in our case, it will be 1. So the important thing here is that, well, we need to calculate the coefficients ci, right? So ci is going to be equal to 2, following this formula that we have here, is going to be 2 divided by b squared, which is 3 squared times j n plus 1 squared, but that is j2 squared, and evaluated at alpha I b, right? But b is equal to 3, so we will have 3 alpha I here. And then the integral from 0 to 3 of x, and then f of x, but that is equal to x, so we will get an x squared here, and then j 1 of alpha I x dx. Okay, perfect. So yeah, the thing here is that, well, we need to evaluate this integral, but how are we going to do this? So we are going to make use of a very well-known formula that involves the derivatives of the Bessel functions with other Bessel functions of different order. That means that the derivative with respect to x of x to the m times the order n Bessel function is equal to x to the m times j sub n minus 1. Okay, so why is this? Because we have this expression here, and we can identify this as this expression, so we can transform this as the derivative of something of this structure. So that is what we are going to do then, to use the fundamental theorem of calculus to erase that integral that we have here. Okay, but first we are going to make a change of variable. We are going to take that t is equal to alpha I x. This tells us that dt is equal to alpha I dx, and x squared will be t squared divided by alpha I squared. And then when x is equal to 0, t is equal to 0, and then when x is equal to 3, t is equal to 3 alpha I. Okay, so we are going to get that ci is equal to 2 divided by 9 j2 squared of 3 alpha I, the integral from 0 to 3 alpha I, and then x squared, but that is t squared divided by alpha I squared, and then j1 of t it will be dx, but that is, well, dt divided by alpha I, right? So here we can simplify a little bit to get 2 divided by 9 alpha I to the third power, just by taking these two elements out of the integral, and then j2 squared of 3 alpha I, and then the integral from 0 to 3i of t squared j1 t dt. So we can easily identify that this element can be seen as this, right? So this can be seen as 2 divided by 9 alpha I to the third power j2 squared 3 alpha I, and then the integral from 0 to 3i of the derivative with respect to t of t squared by using this formula, and we need to raise by 1 unit the index of the Bessel function. So we will have here j2 of t dt. Okay, perfect. So using the fundamental theorem of calculus, we are going to see that we just need to eliminate this integral, this derivative, and then evaluate the t at 3 alpha I. So we are going to get 2 divided by 9 alpha I cubed j2 squared 3 alpha I times 3 alpha I squared, and then j2 evaluated at 3 alpha I. Perfect. So with this, we can get that, well, this 3 squared will cancel with this 9, and then alpha I squared will cancel with this alpha I cubed. So we will get 2 divided by alpha I j2 squared of 3 alpha I times, here we can cancel again, right? So we will get just j2 of 3 alpha I in the denominator, like this. Okay, perfect. So with this, we can say that our function f of x is equal to the sum from I equals to 1 up to infinity of the ci, but the ci is 2 divided by alpha I j2 of 3 alpha I, and then this multiplies, well, j1 alpha I of x. And remember that this is subject to the condition j1 of alpha 3 alpha, right, equals to 0. Perfect. So this will be like the way to express the function f as a Fourier Bessel series. Yep. Recall that it has to do something with a linear combination of Bessel functions. That's the main idea of expressing a function f in terms of this kind of series. Perfect. So the second way is to define a different initial condition or a different frontier condition. Okay, so in the case we want to express the function f of x equals to x defined on the upper interval 0, 3, and we have the condition j1 of 3 alpha plus alpha j1 prime of 3 alpha equals to 0. Well, we need to use a different definition for the Fourier Bessel series. Recall that this is that definition. It turns out that you should notice that here we have the same element. I mean, the coefficient here is the same element that is inside the derivative of the Bessel function, okay? But our initial condition does not have that structure. So that means that we need to multiply by 3 this condition to get that 3j1 of 3 alpha plus 3 alpha j1 prime of 3 alpha is equal to 0. Okay, so with this we have the structure that we wanted, this one over here, and recall that we have a parameter h here. So in our structure, that h will correspond to the 3, right? So we have that h is equal to 3, and then, well, we know that b is equal to 3 also, and again, we have that the condition is subject to Bessel functions of order 1. So that means that our n is equal to 1. Okay, so if we get back to our formula, we see that the coefficients are calculated in this way. And recall that here is a dependence of those parameters that we just talked about, the n, the h, and the b. So that's why we needed to find these parameters. So let me copy this formula, and we are going to develop it furthermore. Okay, so that is the definition of the coefficients of the Fourier Bessel series for this case. Okay, so if we find Ci, it will be 2 alpha I squared divided by, well, b squared will be 9 alpha I squared minus 1 plus h squared, but that is 9 again. And then remember that our n is equal to 1, so we will have here the first order Bessel function, j1 squared of alpha I b, but that will be 3 alpha I. And then the integral from 0 to b of x times f of x, but that is x squared. And then j1 of alpha I x dx. Perfect. And recall that here we have exactly the same integral that we got in the previous example. And recall that this b is equal to 3, right? So I'm going to bring back the result that we found to rewrite this Ci for this new case. Okay, this is what we got for the previous example. And recall that we got a factor of 1 divided by alpha I cubed. And then we made the change of variable t to be equal to alpha ix, right? And we took the derivative of this, right, using the recursive formula that we mentioned. Okay, so in this case, we can use the fundamental theorem of calculus to eliminate that integral and the derivative. And then we can cancel this alpha I squared with this alpha I cubed to get that Ci is equal to 2 divided by alpha I times 9 alpha I squared plus 8 j1 squared of 3 alpha I. And then we will get, well, this thing evaluated at 3 alpha I. So that is 3 alpha I squared j2 of 3 alpha I. Perfect. We can cancel an alpha I from here, yeah, with this alpha I. So we are going to get that Ci is equal to 3 squared is 9 times 2 will be 18 alpha I j2 of 3 alpha I, and then this is divided by 9 alpha I squared plus 8 j1 of 3 alpha I. and this is squared, right? So if we remember, f of x, which is equal to x, can be expressed as a Fourier Bessel series as the sum from I equals to 1 up to infinity of ci times j1 of alpha x, but ci is equal to 18 alpha I, j2 of 3 alpha I, divided by 9 alpha I squared plus 8 j1 squared of 3 alpha I, and then this multiplies j1 of alpha I x. Okay, perfect. So this will be the expansion of the variable x, right, which is the function f, as a Fourier Bessel series. Remember that this is subject to the condition j1 alpha 3 alpha plus alpha j1 prime of 3 alpha equals to 0. Okay, and this is an important condition for this to be true. Okay, perfect. So this will be the final important result. It's just an example of how to express a function f of x as a Fourier Bessel series. Perfect. So I think I will finish the lesson here.